about this here. Okay, let's look at the question together, guys, and then we'll begin. Yes, Darren, you not touch my work again.
I do my work. Is it the 5.3?
Anyways, look at the question here. A student has 5 identical rectangular sheets of paper. The mass of 1 meter square of paper is 0.08 kg. So the first information we have is that 1 meter square of paper is equals to 0.08 kg, guys. Using a meter ruler, she measures the length of 1 sheet of paper and its width. The length is this and the width is this, guys. They ask you to calculate the mass of 1 sheet of paper. Guys, given these two information, this and this, right? How do we calculate the mass of 1 sheet of paper? What's the first thing we do? What's the first thing we do, ladies and gentlemen? Wait, someone knows what to do. We can start with looking for the volume. No, meter square is what? Good. We can start with looking for the area of the first sheet of paper, right? Which in this scenario here will be 0.3 multiplied by 0.21, right? Which will give you 0.063. Is it? This will be in meter square, right? Then after that, what do we do, guys? Once we have this information, how do we compare it to this information to find the mass? I've got times with 0.08. You can't times it with 0.08 because if let's say this was like, yeah, you got to use ratio, guys, mathematically. If 1 meter square is equal to 0.08 kg, how much is 0.063 meter square in terms of mass? You're actually supposed to use it in terms of ratio, guys. So my question is, how do we use ratio to calculate it? I mean, first question first, guys. I want to know, right? 0.063 meter square, will it be more than 0.08 kg or less than 0.08 kg? Definitely less, right? Because here to here is a smaller number, right? Then naturally here to here should be a smaller number also, right? In terms of ratio. So my question is, how much is it and how do I do it? Zero point zero. Let's see. The answer is correct. 0.005. You took it and times, you get the answer. Let's see. Oh, yeah, you're correct. You know why? Because this is 1. By right, you're supposed to play with it in terms of ratio. But so happens this is 1, then you can get the answer. 0.0504 kg. That's your answer. Guys, this ratio, guys, is basically like 0.063 divided by 1 is equals to x over 0.08, which you then find that 0.063 multiplied by 0.08. You'll get your x, and thus your x will have been this answer here. So it's mathematics, guys. Not really at the physics part yet. Okay, everyone. And I want to emphasize one thing, guys. Whenever you write on this dotted line, I'll say this multiple times and I'll catch you guys later on as well. Whatever you write on this dotted line here cannot be more than 3 significant figures, and it must include its units. Like mathematics, I know mathematics usually they'll have like a kg here, then they have a dotted line here, right? And it just asks you to calculate the number, right? Physics is different. If you wrote this without this, you will get 0, not even 1 mark, guys. Good. Next, a student makes a single pile of 500 sheets of paper with a meter ruler. She measures the height of the pile which in this time is 0.048 meters, they ask you to calculate the density. What's the formula for density again?
Mass over volume.
Mass over volume. How much is the mass of 500 sheets? How do I do it? How do I find the mass of 500 sheets, guys? Yep. And the volume will be? How do I find the volume this time? Very good. Is Eugene the only one who attempted? Or is Eugene the only one who is giving me an answer? Then you press in your calculator and you find out the answer. Whatever it is. The answer given is 8.33 times 10 to the power of 2. It's essentially just 833, right? Okay, guys. What's the units for this answer? kg per meter square.
Cube.
Meter cube, guys. Meter times meter times meter. Once again, I want to emphasize, make sure you remember to write your units. If not, it's gonna be a bad time, ladies and gentlemen.
3,300.
What?
3,300.
No, it's 8.33 times 10 to the power of 2. It's 833. Oh, it's acceptable. If you wrote 833, it's the same thing.
So 833
Yes.
kilograms per meter square.
Yeah. Meter square.
Q.
Yes. Okay. Straightforward, easy. The second student is now only has 5 sheets of the same type of paper. So just how this student determines the density of the paper to a similar accuracy. Additional apparatus may be needed. Okay, guys. So right now, right, the situation is when you have 500 sheets of paper, using a meter ruler, I was able to measure 0.048 meters, right? And right now, if I only have 5 sheets of paper, what device am I supposed to use to measure the height of 5 sheets of paper?
Measure.
Have you guys ever heard of something called a
Measurement tape.
measurement tape? It measures up to 100 meters, my friend. So that is definitely not the answer. Have you guys ever heard of something called a micrometer screw gauge or a vernier caliper before?
What is that?
Ah, it's time to educate. Micrometer screw gauge. Gauge. It's called gauge. Yeah. So for those who do not know, right, this micrometer screw gauge is something that is very, very sensitive. When I say sensitive, I mean to say that it can measure very, very small measurements, like literally a sheet of paper. Okay. The next thing up from micrometer screw gauge is what we call a vernier caliper. Vernier caliper is less sensitive. It can measure things that are relatively smaller, but not paper.
Is this the thing they use to make a 3D model? Like,
Yeah, some designers, they use these things to measure the thickness of certain things, right? And then the next thing upwards is basically a meter ruler. So there's 3 things if I measure general length is a meter ruler or whatever ruler that you guys have in the pencil box. Then if I want to measure something that's a little bit smaller, I go to a vernier caliper. And if I want to measure something that's extremely small, I'll measure it with a micrometer screw gauge, guys.
So so he could use a micrometer small gauge.
Yeah. Your answer is going to be use a micrometer screw gauge to measure the height of the 5 papers and measure it 3 times. Repeat and measure it 3 times to get an average. Yes, for those who did not hear what I'm saying, use a micrometer screw gauge to measure the height of the 5 sheets of paper. Repeat the measurements at least 3 times to get the average. And then you get your 2 marks here. Okay, good. Okay, next we move on to the next. Okay, guys, last page before we move on to the next chapter. Define density. How do I define something that has a formula? Very good. Mass per unit volume. Bam, easy. 1 mark. And then next. The density of aluminum is blah, blah, blah. The thickness of the rectangular sheet and foil varies, but much less than 1 millimeter. A student wishes to find the average thickness. She obtains the following measurement: mass of sheet 60 gram, length of sheet, width of sheet. Calculate the student's value for volume of the sheet.
So 50 times 30 times height, but it's less than 1 feet.
Okay, good.
Height is the thickness.
Yeah.
So length, so 50 times 30 times 1.
But it's much less than 1. It's not 1. Nope.
So we need to make this one.
You're supposed to use the density to find the volume. How do I find the volume using density?
Density times mass.
60 divided by what? Very good. You're supposed to understand that given the density and you have the mass, you can actually find the volume, right? Using the formula, density equals to mass over volume. In this case here, my volume will be mass divided by density, which in this case here will be 60.7 divided by 2.7. And press it in your calculator. What will you get?
22.48.
22. No, 48. And 2.5. Why? Yeah, what's the units? How do I know it's cm cube, guys? It could have been meter cube also. How do I know if this question is going to be? No, it's because of here, bro. This is in grams and this is in grams per cm cube. So when you cut it off, ultimately you'll get cm cube. Do you see what I did? Okay, everyone. So 2.5 cm cube. And then they ask you to calculate the average thickness. Now, how do I find the average thickness? How, my friend? Look at the information given and tell me how do I find the average thickness now?
So you pass mass, length, and weight, you divide by 3.
You plus them together. How hard you want me to beat you up? For volume. Plus.
Thickness. But isn't it
22.5 divided by 18.
Yeah, what's the formula for volume? Is what times what times what? Length times width times height, right? If I'm looking for the height, which is the thickness, shouldn't it be volume divided by length times width? Which in this case here will be 22.5 divided by 50 times 30. And you press that in your calculator. And then bam, you get your answer once again. What is it? 0.0? What's the units? Good. Okay. And finally, last question here. The student provides a means of cutting sheet, decides to measure average thickness once again. What's the thing I said just now? What are we supposed to use to measure the thickness? Very good. Micrometer. Is it gauge or gauge?
gauge? You go to Google, you can see the actual what in.
It's gauge or gauge.
You go to Google.
Gauge. You are wrong, my friend.
Gauge.
It's gauge. Okay. Oh my god. Huh? American and British. Nah, don't try to high-tech English me, bro. Gauge, bro. Okay, guys. Any questions from the exercises so far? Anyone has anything that they don't understand? Good. We proceed to the next chapter. Ladies and gentlemen, before you guys frantically copy, I must say don't, because I'll give you time to copy, right? This chapter here, we're going to be learning a lot about forces, guys. In this chapter here, usually students really hate a specific topic on this chapter, which is moments. Both your sisters hated it. So do yours. Guys, I also want to clarify before we proceed on, guys. For moments, right? Moments is just like a turning effect, guys. You know, what are the common turning effects that we use in everyday life? Like this door opening through the hinge there, right? The hinge is acting as a pivot and you have a turning effect that swings the door open. Or alternatively, you could think about a seesaw. A seesaw also has a turning effect because there is a pivoting point here. And when you add some kind of weight, it will turn in a specific side. Same for your screwdriver. Sorry, not screwdrivers. These are your spanner as well.
It's called a wrench.
Or otherwise known as a spanner in Malaysia, right? Yeah, these kind of things. Whenever there is a turning effect, be it clockwise or anti-clockwise, guys, these are all moments. And moments depend on two specific things only: is the force multiplied by the distance. Okay, but we'll go more on that, more detail on that later on. Yeah, this chapter is going to be relatively long. Maybe we won't be able to finish it, but I'll try my best to cover as much as possible. Starting off with the first thing you learn. Once again, these are things that you already learned in year 9. At least I think you've already learned in year 9. Right? Effects of forces could change multiple things, including the shape of a body. the size of the body, the speed of the body, and also direction of the body. For example, if I have clay, I could mold it from circle shape to square shape. If I got a big balloon, applying some force to it could make it into a relatively smaller balloon. If I have some guy running already and I give him a push at the back, he could run faster or just fall to the ground straight away. And ultimately, if there's a lorry driving by and a car decides to smash into the lorry or vice versa, the direction could change. Right? So for forces, it's very straightforward. Nothing much to explain here. Everyone okay? Understand it? Copy this card down first. Oh wait, it's already copied. Good. Next. No copy. Next thing we're going to talk about is basically Hooke's law, guys. I want you all to listen up. Whenever you see this word, right, Hooke's law, I want you all to think about spring. It's always going to be talking about spring or something that is being compressed that will bounce back. Like for example, anything that has a circular, anything that has an elastic body. Don't copy. Listen first. Okay. So everyone here played with a spring before, right? When you compress a spring, you let go, it's going to bounce back. If you elongate a spring, you let go, it's going to bounce back. Have you guys ever tried to pull a spring beyond a certain threshold where the spring kind of just goes already? Have you guys destroyed the spring before?
The slinky counter.
Yeah, it no longer, in the normal scenario, you pull it hard. Sorry, you pull it, let go, it will bounce. You pull it harder, let go, it will bounce harder. And after that, you try to pull it too damn hard, then the spring just go like already, right?
The slinky counter.
Slinky, yeah, same thing also.
Huh? But this one cannot.
Then it doesn't count.
Oh.
Okay, but anyways, you all played with that before, right? So basically what happens is, right, springs are, if you think about it, right, if I elongate it with a certain force, it will extend a certain extension. I elongate with an extra force, it will extend to a certain extension, and then until a certain point. This point is what we call the elastic limit, guys, or the limit of proportionality or whatever they call it now, right? There's multiple names for it. Just know that it's called an elastic limit. Beyond this elastic limit is when the spring no longer returns back to its original position because you essentially kind of overstretch the spring already. Which I'm sure everyone played with before, right? Anyone never overstretched a spring before? Good. Luckily, everyone has some form of childhood.
Can bring nice class.
What?
Can bring a spring neck class.
If you open up your mechanical pencils or even your pens, usually they have a spring inside. I've destroyed multiple of them already. You can try to destroy yours at your own cost, but yeah, some mechanical pencils have spring in it.
Some, okay.
I think yours will have it too.
Every
Mechanical pencil will have it also. If not, why would this thing bounce back? Because of Jesus. I mean, why do you think it bounced back then? Look, I'm pressing it, right? And it's bouncing back. Why? I'll give you a hint, it's not because of God, guys.
Well,
Right. So if you must, I can show you where your spring is. Give me the mechanical pencil. I'll show you. Yeah. Just flick it over. Just like, oh my God.
yeah.
Yeah. So if you want to find out, like, how do I do this? Yeah. Oh, your spring is in the inside. You can't access to it. And it's here. If you look under the light, right, you can see there's like coils here. It's inside, so I can't destroy it for you. Sorry. Unless you want me to. Yeah, so we'll throw it like this. Not like swing it. Like that. This the whole thing just my friend. Okay, anyways. Yes, this guy is eager to this. Yeah, go destroy the spring back at home yourself, okay? Hey, listen up, don't play with that anymore. Anyways, if you play with all the mechanical pencils or pens, they'll have some kind of spring inside one. I've destroyed multiple of them already during my childhood, and you are encouraged to do that on one time. So, okay, put it back.
Yeah.
Okay, anyways, for Hooke's law, you need to remember a few key things. Number one is its formula. Okay, F is equals to Kx, force, spring constant, and extension of a spring. Okay, And then on top of the formula that you must remember the units, which is force, Newton over meter, and meter. I explain later on why is it like that. And most importantly, the thing that you must remember is the graph of Hooke's law, which looks something like this. Yes, don't copy first. Okay, why? Listen up. So it seems that there's a lot of things to memorize, right? Let's go through a simple one first. First and foremost, if we think about a spring, right, we're basically playing with the extension based on the force you exert onto it, right? So if I think about Hooke's law's graph, you must remember that it's a force versus extension graph. And then from here, you think about it logically, if I apply a certain force, it's going to extend a certain distance. Apply another certain force, it's going to extend a certain distance, all the way until you reach something known as the elastic limit. When you reach the elastic limit, the spring is considered to be destroyed, right? So it will no longer be a straight line. It will be kind of like a curved line like this here, right? From here, I can roughly remember the definition and also the formula. Listen up, the definition goes something like this. Hooke's law states that the force exerted on a string is directly proportional to the extension of a spring, provided that the elastic limit is not exceeded. In other words, this part here obeys Hooke's law. This part here doesn't obey Hooke's law. I repeat again. Hooke's law states that the definition is important. You may be asked to write this down, so don't worry, I'll give you time. Hooke's law states that the force exerted on a spring is directly proportional to the extension of the spring, provided that the elastic limit is not exceeded. Okay, let's go one by one and see who here can repeat. I'm telling you. Hooke's law states that the what? No, the what? This one. The force exerted onto a spring is directly proportional to the what does X stand for? Extension of the spring, provided that the elastic limit is not. Very good. Next, guess who? Guess who? You. Can you repeat again? On a spring to the of a spring, provided that the what does EL stand for again? Something limit. What limit? The elastic limit is not okay. You next. Hooke's law state that
The force of the weight is directly proportional to the extension exerted to it, provided that the elastic limit is not exceeded.
excellent. From here, then what you have to remember is that F is equal to Kx, guys. This is the force, this is the extension, and this is Hooke's law, guys. Sorry, Hooke's law. Spring. What? I'm blank. This is a spring constant, guys. Sorry, my bad. This is what we call a spring constant. Now let's think about it logically, guys. This is your first encounter with these kind of random things with random units. If I base my understanding that this is force and this is extension, right? What's the units of force? Newtons. And the extensions unit will be in meters. Then mathematically speaking, right? What's the units of my spring constant? Nm, like this. N/m. Why? Because mathematically, if I have n/m multiplied by m, cut, I'm going to get n, right? Which is what's happening here, right? This is your first encounter with these kind of things. You're going to encounter a lot of random units, including spring constant lah, specific heat capacity lah, and many other things, right? You are actually supposed to derive the units based on the things you already know. For example, you know force is for shear newtons and you know extension is for third meters. Then I know that this will be newtons per meter. Does this make sense or not? Are you paying attention or not? You know what the hell I was just talking about? Yeah. Everyone pay attention. This is important. Okay. Anyone has any questions from this part here? Good. 100% absorption rate. That's what I like. Everyone, copy down everything.
Sure.
Yeah.
And the graph, it says extension is T, so why have they written it as?
It doesn't matter. It's the same thing. All these symbols it actually doesn't matter. If you follow whichever one that you're comfortable with. For me, I've always been doing X from the beginning of time. Hey, draw a graph.
Answer please. Don't be in this. No. Remember.
For those who are not copying, attempt the 4 questions at the bottom. Yeah. Yeah. Thanks.
You don't have to be expert in it.
Guys, I want to emphasize once again. Write down your full formula. It's kilonewton. 1K is 1000.
1 kilonewton is 1000.
Yeah. Yeah, same goes for you also, my friend. You remember to write the formula. What? Not with the KX. Yeah. Yeah. The 94, right? Yeah. Proceed. Okay, more calculator again. Who else can bring the damn calculator to the market to start? Good. Yeah, what?
Yeah, so we pay for the storage speed that is what is the same mountain before the same mountain. That's really important. Actually, let's say this five should be this. If I mean your assuming this should be K, right? This should be X, right? This 5 is your extension, which is here. Then you're looking for K actually. X. Oh yeah. There we are. Yes, my friend. So it seems this is force.
Yeah.
To divide it by 5, or still 6 to times 5.
Still 6 times 5, you only big euro. You're looking for what? Fair enough formula first.
You should check.
Are you looking for which one? F, K, or X?
Things for X.
X, string constant is X.
Okay.
Oh, so we don't want to make 5K. What's the formula to make K the subject? K is equals to
K equals to force divided by 5.
very good extension. 11. Yeah, so this is wrong. I just told you 1 kilonewton is 1000 Newton. Because
Oh, wait. Now, but. The teacher was supposed to have it and be by
yeah, 5 kilonewton.
You think this is zero?
Oh my god. It's crazy to think that looks like a zero.
The five.
It's crazy. It's insane. It's sad. I want to repeat again, everyone. Listen up. 1 kilonewton is 1000 newtons, guys.
Kilonewton.
Yeah, kn. 1 kn is 1 kilonewton, and 1 kilonewton is 1000 newtons. My friends.
So it's like kg.
Yeah, it's like 1 kg is 1000 grams.
So 1 kilonewton is also 1000.
This is. Basically. I'm super big. No. I think the same. Maybe that's medium.
Then line, that's the combination. It's being paid by the one is the boss. No, small, maybe big. The first is 50 keep in the how many liters? Yeah, still is up. In the line, standard. Still. How is the rotation? Yeah, the first thing is to. 50 kilometers is not 10,000. It's 50,000 speaking. Oh, we know. Well, I've seen this design. I'm sure it was the same. Yeah. Let me answer this. One thing is how many? Okay, that's 1,000. 1 K is 1,000, right? Oh, 50K. Okay. Ready for this? Good. We feel true. Yeah. Can I open it? Okay, good. Make it quick. Okay, guys. Yeah. Make it quick. Okay, guys, for those who are not done yet, it's time to check the answers. Okay, so for those who are struggling to complete these 4 questions, it's always good to identify what they want from you and what information is given. In this scenario here, they're asking you to find the force, right? Given the spring constant and given the extension, right? Then actually you write the formula F equals to Kx, and your F would have been 5 multiplied by 5, which will give you 25 Newton. Straightforward. And the same thing for question number 2 as well. This is identified as your force, and this is identified as your extension. You're looking for the spring constant. So if you understand that F is equal to Kx, then K would have been F over X, right? In this case here, it will be 50,000 newtons divided by 5 meters. Yes, and you're going to get ultimately 10,000 Newton per meter. Alternatively, if you wrote 10 kilonewton per meter, is also acceptable. Yes. Finally, the next, oh, sorry, not finally. The next thing is the same as well. You identify that this is your spring constant, and you identify this is your F. Then obviously you're looking for the extension, right? So same thing as well. F equals to Kx. X would have been F over K. In this case here, it will be 10 divided by 10, which will give you 1 meter. Straightforward. And last one as well. This one here, I put a trick on this question, guys. The trick is that they are not the same units, and thus you are not supposed to multiply them together. First and foremost, you should notice that this is in cm and this is in mm. So which one do I change? Yeah, you change this into cm, right? 10 mm is how many cm? 1 cm. So from here, you identify this as your K and this as your X. Then your F would have been K times X. In this case here, it will be 5 times with 1. And ultimately, you're going to get 5 meters at the end of the day. Make sense?
Yeah.
Anyone cannot do these questions?
Yeah.
Very good. Okay. Easy, straightforward. Next part this part is when you have to understand that whenever you apply a force onto a certain object, everything is going to experience some kind of acceleration, provided that there is a resultant force. Let me wait for Leon to come back for this. He went to the toilet.
Yeah, seeing a big.
Huge dump. It's not. I think you're just thinking about it for a while. Everyone, can you all wait 1 minute?
Yeah.
Of course. Of course. I like how when I say can everyone wait 1 minute, everyone immediately whipped out their phone and started scrolling something.
I don't know.
It's a blessing in disguise. Is he actually taking a dump?
Yeah, it's definitely no.
Oh God. Oh well, we'll have to miss this part then.
Good God, your bathroom will start to smell.
It's okay. The toilet, you know.
Can wait. Yeah, can wait.
Of course, you all can wait. Okay, I'll wait 1 minute.
That's a little bit out. That's not. So I get you. So I. You know, you're. So then just so that too. Yeah, it's not. You know, it would be. Yeah. That's actually over there. Still up here.
Sadly, he will have to miss it. It's basically studying resultant forces, guys. If you think about it, anytime we apply some kind of force to an object, you're actually supposed to cause it to accelerate, guys. Now, but if you, with that in mind, right? Yeah, with that in mind, right? If you think about your current position right now, let's imagine this is a poorly illustrated chair, and this is a poorly illustrated ass, leg, body, and hand, right? Your ass is essentially applying some kind of force onto the chair, right? Guys, listen up. Your ass is applying some kind of force onto the chair, right? Which is, let's just say that if your average is about 50 kg, let's just say you're somewhere around 500 newtons. My question is, how come you're not accelerating downwards if you're applying a force downwards here? Very good. The chair is actually applying an equal and opposite force of 500 newtons as well. So what I want to show you here is that
although it is true that when I have a resultant force applying onto something, it will cause that object to accelerate. But you need to understand when will it be a resultant force. For example, if today I have a block here, right? I pull it with 100 newtons, and then here I pull it with 60 newtons. Will it accelerate? Why?
Because you're not done.
Yeah. So basically, there's a resultant force of 40 newtons to the right? And this resultant force is the one that causes it to accelerate. Alternatively, instead of being 60 here, right, here is 100.
It will not move.
It will either not move or it will remain at constant speed. For example, you know when your parents drive on the highway and then you see the speedometer is like 120 km per hour and it doesn't increase nor decrease, right? This is when the force from the engine forward is equals to the frictional force backwards from the tires, guys. At this scenario, you could either remain stationary or you could move at constant speeds. Guys, these are the two scenarios. And ultimately, of course, let's imagine today your parents are driving a car and then suddenly in front of the road, she sees once again another innocent Paul standing on the road. Then what's going to happen is your parents are definitely going to start jamming the brake, right? When your parents start jamming the brake, then obviously your backward force will be greater than your forward force, right? What's going to happen here?
Stop.
Before it stops, certainly what will happen?
Screech on the ground.
If the, yeah, it's going to decelerate, guys. That's why your speed will slowly, not slowly, it will decrease really fast unless you smash into Apple and send her directly into heaven. Apple, meaning like a grandmother. Damn. It's getting dark in here, guys. It's getting dark in here. Okay, anyways, yeah, this is the scenario, guys. So you must understand what a resultant force is. A resultant force is the extra forces acting on an object which will cause it to accelerate. It may not necessarily be when there is force, there will acceleration. Now, for example, when you're sitting down here, although there is force, there is an opposite and equal force. Then obviously you're going to be remaining stationary. Yeah. Very good question. So what happens is, right, imagine today it is no longer just you sitting on a chair and it's some really happy person who enjoys all his meals. Who enjoys his happy meals for sure. So let's imagine today this guy is applying 1000 newtons and this is a shit chair, by the way. Let's say it's a shit plastic chair. And this chair can only apply, apply a force of 500 newtons. Then what happens right now is there will be a resultant force of 500 newtons downwards, right? Then what's going to happen is this chair is going to break. Yeah, the chair is going to break and it will cause this guy to accelerate downwards. Until it hits the ground. Yes.
Then how do some chairs like very like regular chairs also can somehow sustain the weight of the
Oh, very good question as well. Okay, so some chairs, they look flimsy, but they actually can withhold damn a lot of weight. Why? Is because they are engineered to withhold a lot of weight. If you guys ever notice, some of those chairs, right, they apply a lot on the triangle. They apply a lot of the triangle weight balancing on the, you know, like sometimes on the, if you see those really long bridges, right, they won't be like one line and then all the cars going right, it'll be like triangle, then triangle, then triangle, then triangle, then triangle.
to make it more reinforced.
Yeah, this is actually an engineering reinforcement that actually distributes the weight more equally. Right. So even though it's a really shit chair, but it can still distribute the weight very much equally and thus sustain it. Later on, when you guys go to uni, if you guys ever do engineering, all the engineers will do the same thing. The first year, you guys are asked to build a bridge made of popsicles. And this bridge, right, is supposed to withstand as much weight as possible. For my year, when we did our engineering first year, this guy, he built a bridge that could literally withstand 2 people standing on it. And it was made from popsicle sticks. So that guy was a good engineer.
I think I saw someone do it with pasta noodle. So
pasta noodle will be the same application, but you have to tie more of it. Yeah, so it's not about the material, it's about how you engineer it. That's why engineering comes into play. Engineering, like all physics and mathematics, is the efficiency of maximizing everything to the finest. You know, so it's not like, oh, you want to go 500 kg, just buy like 50 tons of steel to reinforce, then that's not called engineering, right? It's just like you got money, then you can use excessive amount of metal to reinforce the 500 mark. So this is where engineering comes into play. You use the least amount of material with the best amount of results. That's engineering. Okay. Anyways, moving on. From here, you should remember one very important formula: force is equals to mass times acceleration. For example, if I apply a force of 100 newtons on an object, a resultant force of 100 newtons on an object that is 10 kg, it will actually cause it to accelerate at 10 meters per second squared. Okay, this force is not just any force, it must be the resultant force. For example, in this scenario here, right? Let's say the resultant force here will be how much? 900, right? Let's assume that this thing is 100 kg. It will cause the thing to accelerate at 9 meters per second because F is equals to ma. Make sense? Yes? Accelerate, decelerate, constant speed, or stationary because there's no resultant forces. Okay, copy down the formula and attempt the 4 questions at the bottom once again.
If 100 kg is like 1,000, right?
Sorry, what?
130 equals to 1,000.
Yeah, 1 ton is 1,000 kg.
Thousand kgs is how many meters?
Sorry?
1,000 kgs is how many meters?
kg meters.
Yeah, kg is meters. 1,000 kgs. Meters into unit.
I don't know, why don't you tell me?
So that's
How do you convert mass into length? How heavy are you right now? Can you convert your mass into length?
To find the mass, we need to force divide by acceleration. Okay.
Hey, how many times do you want me to say this? Write your damn formulas down.
If it's like 33.33,
Write your three significant figures.
33.
Yeah.
H.
Also, obviously, but it's not law. Give me 1 minute. Yeah, I think the name. In the law, I never did it all.
And a lot of components.
Yeah. I don't see.
And now, go to the station. Do the backs, the one, the front speed, right? Of it. Of it, well, it. I didn't. The uneven explanation for the KGM, KG. But any more people, they had. With others. Wait, first,
What the other problem? Very good. Seven. Stupidity. Stupidity happened. Yep. Yeah, the door was latched and she thought it was locked. And she just stood outside and told us it was locked. Anyways, same thing, guys. It's the same application over and over again. Now, first and foremost, you understand that 1 ton is equals to 1000 kg. Right, you're asked to find the force given the mass and also the acceleration. Very straightforward. F equals to ma. Yes, and then it's going to be 1000 multiplied by 30, which will give you 30,000 newtons. Straightforward and easy. Next thing, you're going to find for mass, you are given the force and you're given the acceleration. So in the same scenario here, Fm will have been F over A, guys, which have been 1000 divided by 30, which will be 33.3 kg. Same thing for this one as well. Find acceleration given the mass and the force. Acceleration is force over mass. In this case here, will be 500 divided by 50, which is going to be 10 meters per second square. Right, and finally, find the resultant force generated from a plane moving at constant speed. The answer is a big fat 0. Same thing. Zero by 1, wrong. This is your force, right? What? Say that again? 500 divided by 50, how to be 0 by 1? It's a bigger number over a small. It's a bigger number over a smaller number, isn't it? Okay. Okay, can everyone? Any questions? Ooh, you guys want to make my life easy, is it? Okay, last part of the day. And then I'll let you guys rest for. I don't want to start this because of the time, guys. I don't want to start this here this week. Let me just talk about the last thing, which is circular motion, and then we'll end the day. Okay, guys, listen up. For circular motion, right? I want you all to know that this is literally free marks. Free marks. Whenever you see anything that is moving in the circular motion, right? I want you all to remember that the acceleration and also resultant force is always towards the center of the circle. You know how will the question be like? They'll give you something like this. A car is traveling around a circular track at a constant speed. In which direction is the resultant force? And the answer in this scenario would be yay, 3 marks. Every year is the same question. Same damn question every damn year. So why is it towards the center there? Let's look at something more relatable. For example,
the moon and the earth and the stars and the universe. Okay, let's imagine today this is earth. Okay, and we know for a fact that the moon would orbit around the earth, right? At this position here, it'll orbit and it'll orbit and it'll orbit and it'll orbit and right. I'll just draw the 4 different positions up. Today, I know for a fact that this moon is actually moving in this direction. But there's something in between the moon and the earth. What is this called? Very good. It's known as the gravitational pull. And I know for a fact that gravity is the same as... No, gravity is the same as what other component? That has the exact same units also. What? What's the units of gravity? 5.8 what? Meters? It's not. Good. The answer is acceleration. Meters per second square. Why? If you look at here, right, gravity is meters per second square. And acceleration is also meters per second square. From here, I want you all to remember that gravity and acceleration are kind of the same thing, guys. Just that gravity is always downwards and acceleration is in literally any other direction. Okay? So first things first is because the moon is moving in this direction and there's gravity pulling in this direction, what happens is there'll be a resultant velocity in the middle here, which gives rise to this red color line here. It's the same thing here as well. The moon is actually moving in this direction, but there's acceleration pulling in this direction, so it gives rise to this middle here. Same thing here as well. Acceleration towards the center of the circle, moving in this direction, give rise to this middle velocity here. Same for this one also, moving in this direction, accelerating in this direction, and I'll have a velocity here as well. Okay, so from here, what I want to actually show you all is that whenever anything is moving in a circular motion, the acceleration will always be towards the center of the circle. And since we learned that acceleration is due to force, right? Then naturally, if acceleration is towards the center of the circle, then resultant force should be towards the center of the circle as well. You all understand what I'm talking about? Yes, right. Let's imagine today, right? Suddenly, Earth's gravity shut down. What's going to happen to the moon? Yeah, it will literally fly in this direction. Can you imagine, have you guys ever swing something above your head before in a circular motion? Imagine if someone cut the string suddenly, right? What's going to happen is the string, the whatever object will just suddenly fly into one direction, right? This will be the exact same scenario as well. Okay, so in order to continue the moon circulating around Earth, it must have a continuous acceleration or gravitational pull towards the center of the circle. Make sense, everyone? And because of that, if you ever see anything, the question will be something similar. They'll say something like, oh, it's bending through a curve lah, or moving in a circular motion lah, or whatever lah. Then they'll always ask you, where's the resultant force? Where's the acceleration? The answer is always towards the center of the circle. Easy, 3 marks. He's gonna die soon. Make sense, everyone? 3 marks, don't lose it. In fact, when you guys go for your exam, I'm sure this will come up as well. Okay, that will be it for today for physics. You all may take your 15 minutes rest and we'll continue with chemistry at 3:30. Hey guys, Caden and Max, you guys got any questions?
Am I supposed to leave?
Oh yeah, that's it for today. I'll see you next week.
Okay, bye-bye.
Bye-bye.